Hi, I'm Jack, and this is my Lab4 report. In this lab, we are exploring how current flows in a simple circuit. So if we generate electric potential using a chemical reaction in a battery, we can form an electric field through a conductor between the battery terminals. That electric field will then move electrons or electricity. We use a couple basic rules. First, the node rule tells us that at any point, current in equals current out, or in other words, in a loop, the current at every point will be the same. We'll also use the loop rule, which tells us if we assume a battery, for instance, is positive voltage, the voltage will drop across all the resistances. So by the time it gets back to the battery, we're at 0 volts, or the sum of all delta V's in the circuit is 0. These help us figure out Ohm's law, which tells us voltage equals current times resistance. So given this simple circuit, we can use the previous simple rules to calculate the current and voltage. Because they're in series or in one loop, we can figure out one effective resistor with a resistance of 147 ohms, or the sum of these two. Using Ohm's law, we get the current is 0.0204 amps, and using the node rule, we know the current's the same everywhere, so both ammeters will read 0.02 amps. When we simulate it, that's exactly what we get. If we connect the meters backwards, the current is flowing in the other direction, so the current's opposite or negative. This simulation doesn't show sign, but it's basically the negative current. So if we replace one of the wires with the voltmeter, we'll notice that the current drops to 0, which tells us that we open the circuit. In other words, the voltmeter has infinite internal resistance. Because of this, the circuit's effectively open. Because it's not complete, there's no current to flow, so neither the loop rule nor the node rule apply. That's why the voltage isn't dropping in this case. It's still at 3 from the batteries. So if we connect that back up and then just use the voltmeter in parallel to measure the delta V across each component, you get this diagram here, and we'll notice that the sum of all voltages is 0, which makes sense from the loop rule. And the current's still 0.02 amps because we haven't changed the resistance in the circuit, because the voltmeter has infinite resistance, and so it's not adding any loops or nodes to the circuit. So what the meter's doing is reading the difference in voltage between 2 points. We attach the black to the negative end of the battery, and we treat that as 0 volts. Then the red lead will read the absolute voltage at every point. So it starts off at 3 from the battery, and as we go across our resistors, that slowly decreases back to 0. It doesn't go below, but it goes back to 0, which is what we'd expect from the loop rule. When we attach the voltmeter, the ammeter reading doesn't change, like I said, because it's not adding any loops or nodes to the circuit. No current is flowing through the voltmeter. When we replace the voltmeter with an ammeter across a 100 ohm resistor, it creates a short because the ideal ammeter in this simulation has no internal resistance. So basically all the current will flow through that, and it's like we got rid of the 100 ohm resistor. In real life, no ammeter is perfect and won't have 0 resistance, but it's still so low that it'll effectively give us the same result. So now we'll switch to RC circuits and charge a capacitor through a resistor, in this case a bulb. With an uncharged capacitor, the current will start really high, the bright bulb, and then decrease to a dim light as the capacitor charges. If we connect the charged capacitor to a bulb, it'll discharge through the bulb, start bright, and run out of potential and dim. We can time the charge and discharge times. They should be the same with a given resistance, charge and discharge, because of the law of conservation of energy. If we double the resistance, half the current and the time should be double, which is roughly what we get here with these timings. So now we'll time a little more carefully. Charge a capacitor directly with a battery, which in the simulation charges instantly because there's no resistance. In real life, the wires do have a little bit of resistance, but it's still so small the capacitor charges very fast, which means for that brief moment of time the current's very high, which will generate some heat and can damage some components, but that's not a factor in this simulation. So we'll start with the loop rule in this first line and convert each of those delta V's to the definition, the capacitor formula, and Ohm's law. We don't know Q, so we write it as a differential equation, solve the differential equation, and then take the log of both sides. If we forward that here and graph the results, it's linear, which is nice, and using a regression we can get the slope. If we look at our formula, we'll notice the slope is -1 over RC. If we treat the x-axis as t, and we can, using the regression, solve for RC and get RC equals 6. If we just compute it by hand, RC is the resistance times capacitance, or 30 ohms times 0.2 farads, 6, which means it takes 6 seconds for the capacitor to charge a significant amount, which proves the equation. So that's just a little overview of circuits and RC circuits. Thank you for watching.